Here's a good puzzle. It comes out of an old Sherlock Holmes story. Looking at the tracks from a bicycle, can you tell which way the bicycle went? Why not pause this video and figure it out? Did the bike that made these tracks go to the left or to the right? Okay, we're back. Before I tell you the answer, let's ask a more basic question. Which track is from the front wheel and which is from the back wheel? And I think some of you didn't actually pause the video for my first question, so I'm going to give you another chance. I want you to pause now, look at the tracks, and answer two questions. Which track came from which wheel, and did the bike go to the left or right? Okay, have an answer? I like this puzzle because it leads you to ponder some notions from a branch of mathematics called the differential geometry of curves, which originated with the beginning of calculus in the 1600s. The key observation is that the two tracks are not independent, like, say, two unicycles would be. The front and rear wheels of the bicycle are connected, and that constrains the possible shapes of the track and how they relate. You can steer the front wheel in any direction, but the back wheel always follows a fixed distance behind. So how do you see that in the tracks? To get the essence of the idea of following a fixed distance behind, just experiment by pulling something. Back in the 1600s, this was demonstrated with a pocket watch on a chain. And I'll use this keychain flashlight in the same way. As I pull the end of the chain, moving my finger along a straight line, the mass follows a curved path, getting closer and closer to the line, but never reaching it. This curved line is called a tractrix. The track part comes from the Latin word for pull, as in tractor. Newton first derived its equation in 1676, and the straight line here is called the asymptote to the curve. The key notion we need from differential geometry is that of a tangent line. At any point of the tractrix, you can draw a tangent line. Then if you go forward along the tangent a fixed distance d, that's the length of the watch chain, you hit the asymptote. A bike moves in the same way because the motion of the back wheel is always aimed towards the position of the front, a fixed distance away. Now you can't push a pocket watch chain, they can only pull. So you actually miss half the tractrix if you just pull in one direction. The complete tractrix has two branches connected at a cusp. A bike frame can both pull and push the back wheel, so watch what happens as I move the front wheel along the line. The back wheel moves first along one branch, being pushed, then along the other branch, being pulled. Well, my bike track here isn't exactly on the prediction, but it's close enough to give the idea and show what happens at the cusp. I should tell you that to make this work, I chose the size of my tractrix, so the distance from the cusp to the asymptote exactly equals the wheelbase of my bike. That's the distance between the points where the two wheels touch the ground. Then because it's a tractrix, the distance from any point of the curve to the asymptote, measuring along the tangent line at that point, is constant. Incidentally, this pushing aspect to half the curve means that the Latin track for pull is something of a misnomer here, leaving out half the fun. So maybe they should have come up with some better name for this curve, but we'll stick with tractrix. Now, one reason the back wheel didn't exactly follow the curve is that the wheelbase of a bicycle isn't quite constant. Depending on whether a bike is designed for racing, touring, or utility purposes, frame designers carefully set the fork at an angle from vertical, and they set the front axle slightly forward from the steering axis. These factors determine stability and cause the wheelbase to change slightly when you steer and as you lean during a turn. But a simple mathematical model can ignore such real-world details if we still get good insight into what's happening. So for analyzing the bike paths, we'll just assume the distance is some constant d. Moving the front wheel in a straight line to generate a tractrix was just one special case of what a bike can do. Let's look at another case where you steer the front wheel with some periodic oscillation as you slalom down the road. The back wheel will follow, making a path with the same frequency but smaller amplitude. After the bike is gone, the back wheel track is easy to identify. It's the one with less variation. So given just the tracks, how do you know which way the bike went? You can first look to see which track has more variation. That's the front wheel. Here it's red. you can take any point on the other track, the back wheel path, and draw a tangent in one of the two directions to see how far it is along the tangent line to the front wheel path. If you choose the right direction, you'll find that it's the same distance no matter which point on the back wheel path you start from. But if the distance varies, you must have chosen the wrong direction, so try going the other way on the tangent line. In the direction corresponding to the motion of the bicycle, this distance is always the same no matter which point you start from on the back wheel track. And if neither direction works, then Sherlock Holmes should be able to deduce that it was two unicycles who rode by. And then a mathematician sees one other case to consider. What if both directions work? That's mathematically possible in a special situation. If you ride around in a perfect circle all day. The back wheel then makes a slightly smaller concentric circle from the front. The picture is symmetric, so you can't tell if the bike went clockwise or counterclockwise. But if you have a typical path with varying curvature, you can always figure it out. First, identify the rear wheel track by its smaller variation. Then look at the tangents. Here, the tangents going left would have different lengths, and so the bike must have gone to the right. Be sure to look for bicycle tracks whenever you're walking around outside. Think about the tangents, practice your deductions, and you'll know where to find the bicycle.